minus the integral of v du. Or what, ultraviolet minus, this looks like voodoo. Anything helps you remember this. I put down this acronym LIPIT. If you just want to have an order of like, what should I let the u equal to when I do these problems? In order of preference, L stands for what? Logs. I stands for inverse trig functions, like that arctan we had over there, that inverse tangent of x. P for polynomial, that could be just like a letter x, or an x squared. E is like e to the x, exponential, and t would be last, just being a trig function. So you'll notice today, if we got something, we're doing the integral, and it's got a log, natural log combined with a trig function, then we'll let the u equal to what? Natural log. Cool. Hey, I like to throw across the board, when do you need these? A lot of times they're easy to recognize in later math courses. I'm just going to throw a bunch. And then we'll solve some. But I just want to throw a couple of these, like, okay, x to the 2x. This is where you need integration by parts. You might notice a pattern to this. Sine of 2x. Just common things that come up in, I teach Calc2, and this is what we see. And we go, oh, we need integration by parts. And there's no doubt about it. I can just put 5 up here. X, e to the x. Here, I'll put a 2 in front of here. I'll put an 8 in front of here. These are just some common expressions I thought I would just throw at you. And you go, how am I going to be able to recognize when to use integration by parts versus a u sub throughout this course? A lot of times it's easy to identify. You see how there's no like x squared with an x? We saw that with u subs, didn't we? X e to the x squared. You bet it is a recognition game. Isn't that a u sub? What would you let u equal to? X squared. And so these, they kind of stand out. X trig function with another x. X e to 1, it's got an x. X e's got an x. X cosine, it's got the x. In later math, or like Calc2, you'll be able to recognize these. You'll be able to recognize, I'm going to have to do integration by parts. Usually, not all the time, but u subs have that power difference by one integer. I know it's not always, but it's very common, so you can identify that. All right, well, let's do one. Let's do one like this. I'm going to pick one like this. The one in the book, and when I noticed to use the variable t, so I'm going to use the variable t. All right, so let's do t sine 6t. And we're going to find the integral, find the antiderivative. And we're going to use integration by parts. So, we just go off to the side. Integration by parts, IBP, huh? It's not a u sub, it's integration by parts. I have to let u equal something, and I have to let dv equal something. From that expression. Because it's integral of u dv. Does everyone see that? We always let u equal something, we'll take the derivative of it and get a du. We'll let dv equal to one part of that expression up there, and we will take the integral of that. So hey, according to LIPIT, what would you let u equal to? The sine of 6t or just the t? All right, the u is just the t. So what's the dv have to be? Everything else, which is the sine of 6t dt. So far, so good? Hey, if you're good with derivatives and like u subs, it's smooth sailing now because you're just putting it in a formula. Well, let's see. What is the derivative of this t? Just one, right? And I heard someone say dt, so I'm going to put it next to it. Because you'd say, all right, the derivative of that with respect to t would be 1 dt. What's this integral? And we were just doing this in the warm-up.
You gotta do a u sub.
It requires a u sub. But feel free to think it as that formula. What would you use for that formula?
That's 1 over the inside.
1 over 6 by a u sub, and then the cosine of the 6t will be positive or negative?
Negative.
So I'm going to write it down. It's going to be negative 1 over 6 cosine of 6t. That's the integral of that. Yeah, the integral sine is negative cosine. We have this SC, SC, S. These two negatives on the third and fourth help us know how to do integrals of sines and cosines. this required a u sub though, we would have let u equal this 6t, done all the work, and that 6 would come out there in the denominator as so. Hey, so if this was sine of 4t, wouldn't this become negative 1/4 sine of 4t by a u sub? I do want to emphasize though, a u sub was used here. So if you're still struggling with that u sub method, and I didn't even write it out now, feel free to see me after class to work a couple more of those out for you. All right, it's ready to plug it in the formula. So ultraviolet minus integral voodoo. All right. UV, what's the U? T. The V is the negative 1/6 cosine of 6t. I'm going to put a parentheses around that because it was negative. Because eventually, where should I put this minus? Yeah, I get a lot of students, they leave it there in the middle, and sometimes if they don't put the parentheses, they can lose points, because it looks like t subtract 1/6 cosine 6t. So eventually, that's why the parentheses here, I'm going to put that minus, and I'm going to put it right in front of this t as the coefficient. All right, now I got a minus integral, the v is negative 1/6 cosine of a 6t, and then the du is just the dt, there it is. Hey, I'm going to rewrite this, because what's a minus minus? So here comes the rewritten expression, negative t. You can put the t over the 6 if you want. Cosine of 6t plus integral 1/6. Do you like to put the 1/6 out in front? Okay. Cosine of 6t dt. Don't leave the answer like this. We still have to just do that little integral. By golly, didn't we already do a u sub already in this problem? We already did a u sub to take care of that. We've got another u sub, don't we? So that's what I mean. You'll find these integral of cosine 6t again. I'm doing a u sub like this. Now let's write that final answer. Negative t over 6 cosine of 6t plus, okay, the integral of cosine, is it positive or negative sine?
Sine, positive.
Positive, okay. And I got a 1 over, I'll put sine of 6t. Now help me out. This was a 6. Well, what's going to happen to that 6 by the u sub? It'll get multiplied to that 6 in the denominator, making it 6 times 6? 36. There you go. And if you want to factor, you can, but you do not have to. That's the expression. That's the antiderivative. And if these had, what, a 0 to a pi over 2 or something, then we would have done a definite integral like we usually do for the whole expression. Well, right now, before we start, we know how to plug numbers in. We know how to plug numbers in, right? We know how to do the definite integrals. We need to focus some time on what's the different type of scenarios we'll see. There's one common one, right? And 2 times we had to do this u sub in terms of an integral. Did you spot that? Just out of that problem. Cool. And I always like to say this, you got extra time on the test, can you check this? It may take a few minutes, but how would you check it? Take this answer, take the derivative of all this, and what should you get? That. But you have to do product rule there, right? You have to apply chain rule here. While you're doing product rule here, you got to apply the chain rule. So I get it. It would take some time to do that, but you would find that you got the answer done correctly. Any questions on this? Hey, excellent. That's a common type, everyone. From the textbook, that's kind of like number 3. It's also like number. It's also like number 23. Number 23 is a definite integral in the textbook. Number 3 was an indefinite integral like this. Cool. So good practice problem for you to work later. Let's try another one. You've probably never seen this before. What was the derivative of natural log of x? Here I am doing a curveball at you. What's the derivative of natural log of x? 1 over x, right? But up until now, unless you've seen integration by parts before in another math course, like a Calc2 course that included it, we haven't done this before. We've never integrated found the antiderivative of natural log of x. And I wanted to let you know, it involves integration by parts. You need integration by parts to do this. So I'll get this out of the way. We're going to find the integral. We're going to find the antiderivative of natural log of x.
Can you put bounds on this one just to see what we should do with an actual?
Absolutely. Hey, we'll work it all out, and what I'll do is when I'm done, I'll take off that plus c, and you and I, let's put some numbers in here. I won't use 0 because the natural log of 0 is undefined, but I'll definitely use like a 1 and a 2 in there, and we'll put the answers in there. And that's a great call. The last one we did was indefinite. We'll do another indefinite, then when we're done, let's put some numbers on there.
Thank you.
You bet. All right, you know the deal. I gotta let u equal something, and I have to let dv equal something. By the way, do you know why I do corners here? Because I want to emphasize this, you're doing what? Taking a derivative, and once you put this in place, you're doing a integral. That's the only reason I write it this way. Just to remind you, I didn't want you to think you're doing 2 derivatives over here, or 2 integrals. Once you plop something in here, you take the derivative. Once you plop something over here, you're taking the integral of it, or the antiderivative. All right, according to Lipit, what shall I let u equal to?
Natural log is.
Oh, you're good. Natural log of x, okay. And we'll get the derivative in a second. So what's the dv? 1 dx, okay. Hey, I'm gonna start with the easy one. If this is 1 dx, what is the integral of 1 dx? It's not 0, because you're doing an integral. It's x. Okay. And what's the derivative of natural log of x?
1 over x.
1 over x. Ooh. And it's ready. And then put, yeah, I like that. Let's put the dx there. Even if you forgot to put the dx here, you'd still write it in yourself. Very good call. All right. uv minus integral v du. What's the u? Ln of x. What's the v?
X.
Can I just stop there? Look how I wrote it so far. And when I don't want to write ln x, x, wouldn't that look weird? Look. I really like that. And that may confuse you. Like, what does that mean, right? So I'm emphasizing we're going to do the natural log of x times x. In fact, what's a better way to write that?
X natural log.
He says better to write this as x ln of x in the end. Good. What's the integral of a v? Right? We got uv minus, oh, I put a v. What was this? This v was just an x? Ooh. So we got natural log x times the x minus the integral of the x times du, which, what's du? So there's the v. There's the v. I'm going to substitute the du now, which is 1 over the x. The x right there. Put the du. I just want to point out where each two of these two parts are coming from our work on the side here. So what's x times 1 over x? So we're going to now get x natural log x. That's a better way to write that. Minus the integral of a 1 dx. So what's the integral of 1? 0? No, that's the derivative.
X plus c.
X ln x minus x plus c. And we'll take Connor's advice. Once you all have that, let's go back and put some limits on here. He's recommending, he goes, no crazy numbers, just give us some numbers so we know what to do to get evaluated definite interval. Because we know we put the 2 numbers in and we put in the top number, then we subtract it and put the bottom number in there, right? Okay, cool. Anyone okay with that? All right, now extension. How about a definite number? 1 and 2. So I'm going to take out this plus c. We don't need the plus c, do we? For definite integrals, we don't need the plus constant. You could write it, but wouldn't it, when you subtract, a c minus a c becomes what? 0. So just go away. All right, let me get down to here. You can keep writing that 1, 2 through all these. But eventually, you're going to get down to this antiderivative expression, and you're going to plug in a 1 and a 2.
First, I noticed that whenever you do this part, the du and dv to v, you never, since it is indefinite integral, you never include the plus c. Is that just shorthand, just for you, or on
Oh,
the
great
integral?
question. Yeah, so right over here, he says right here, I'm actually doing an integral. He goes, well, you're integrating this, you should put a plus constant. You can definitely write it there if you want. It is shorthand, because I know eventually I'm gonna put it here.
Okay.
So really good. If you want to write it here every time and then just transfer it, very good. All right. What do we get? You ready, Connor? Everyone ready? I get 2 natural log of 2 minus a 2 subtraction. Now what do I have to plug in there?
Parentheses.
Parentheses, brilliant. Put a parentheses so we don't mess up the distributive property. Now substitute the 1. 1 natural log 1 minus 1. And let's see what we get. Does everyone know why I didn't use 0? Natural log of 0 is what? Undefined, right? And later on in our course we talk about improper integrals. That topic comes up, but not now, so it's like, let's go from 1 to 2. All right, what is natural log of 1? Natural log of 1 is 0. Somebody rewrite this. I've got 2 natural log of 2 minus 2. Whoop, minus parentheses, that's just a 0 right there, but you do have this minus 1 here. So help me make that just a tad prettier. 2 natural log of 2 minus negative 1. Well, that's 2 natural log of 2 minus 2 plus a 1. Because a minus and negative 1 is a plus 1, right? So what would be the final simplified answer? I'll put it right here. 2 natural log 2 minus a 1. And what's so cool about this, everyone, is even your TI-84s, if you put this into the definite integral program in your calculator, it's not going to give it as an exact answer. That's exact. You know, put approximate in terms of an irrational value. That's just the places, numbers out there, decimal place. Keep going. That's exact. Hey, does anybody like to move the 2 up here and make it L and a 4? You know that property of logarithms? That you can move this coefficient right there, natural log of 4 minus 1? I think that's important to discuss, because I don't need someone like during the weekend here stressing out for 2 hours thinking you did a back problem wrong because you got this. And I'm going to call backup book Bob, okay? Bob for backup book. The back of the book says natural log of 4 subtract 1. You go, what did I do wrong? You did nothing wrong. They just moved this 2 where? Right there. It's a property of logarithms. You know, just coming from pre-calculus. I do want to point out, you can leave it like this too. This is really nice. Natural log of 4 subtract 1, or 2 natural log of 2 minus 1. Great. Well, let's do another one. Hey, before I do the next problem, I just had a question for you. One of the problems that I put for practice it's in the integral of an x squared and a natural log of x. We won't do it now. I was just curious. According to Lect, what would you let u equal to? The x squared or a natural log of x? Natural log of x. Very good. I just want to point that out. No question. Okay. All right, we got to do one of these. Inverse tan of x dx. We've never done the integral of a natural log before. We also never done the integral of an inverse tangent expression. Hey, just so you know, I don't know if everyone's aware of this, there's another way this can be written. So I'm going to write it like that. That's another notation for inverse tangent of x. Arctan x, it's another way it can be written so that you're familiar with that. Just in case you came from some Calc1 course, pre-Calc1 course, and some of them are using a textbook. There's some textbooks, they may note this somewhere, but then they use this throughout the whole textbook. So you're aware of that. Okay, well, this time I'll just use it in this expression. We'll do another one. The next time I write this, I'll use arctan. All right. So I'll write it like this. According to Lect, what should I let u equal to? Let's see. Is there any logarithms? Nope. Are there any inverse trig functions? Yes. It's the inverse tan of x. So that's what I'm going to let u equal to. The inverse tangent of x. So there's a challenge line ahead. Do we know how to take the derivative of an inverse trig function? The inverse tan of x. So that's going to be coming up. So what's the dv equal to? X. The VE is just, not even x, just the what? Just the dx, right? The 1 dx. So when we let this be the u, and so the only thing left over was that dx, the 1 dx, that's going to be our dv. U is this, dv is that. Integral, derivative. This is easy. Let's do the easy one first. What's integral 1? Just x. We have to put the plus c, we'll be dealing with that later. What's the derivative of inverse tan of x?
1 over 1 plus x squared.
Really good. Yeah, that's the derivative of inverse tan of x. 1 over 1 plus x squared. Oh, cool, we didn't have to do chain rule. Let's do that next. We'll do one where we had to do chain rule in that. But right now, this is what we got. Let's go find the antiderivative. U, v, minus, integral, VDU or voodoo. Great job so far with integration by parts. IDP, right? I see this. I'm taking a differential equations course. I'm like, oh, that's integration by parts. I have to use integration by parts. All right, the U is inverse tan of x. The V is just a what?
X.
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 Where would you write that x? That's a great idea, everyone. For right now, I will put it here so it lines up in your notes, but eventually it's better to write x before the inverse tan of x. It looks better. I didn't want this x down here. It looked like you might have done x times an x. Very well. Right now, I'll just think, all right, you had all this. Multiply to some x, all right? Minus integral d, and du is, wow, and I didn't even put the dx here, I apologize. You know, it's 1 over 1 plus x squared dx. So I'll put that right here. Times 1 over 1 plus x squared. If the hard part's over. This is, you're looking at this and it's scary, this is not going to be bad at all. I'm just going to rewrite that. X inverse tan x, so I can just write it like that. This looks better. And maybe I'll write this like this. Just put the x in the numerator now. Almost done. Hey, the student left the answer like this on the test. It gets some partial credit, true? I mean, golly, they got everything done. Maybe they just got stumped on how to do that integral. Right? And they're thinking, is that another arctan or something? How do you integrate that? That's not so easy to spot. It's not another integration by parts round. I didn't want you to think that. Like, we got to do integration by parts again? Not in this problem.
It's a natural log.
It's a natural log. It looks like a natural log. So I know it totally looks like one. This is a natural log. By golly, it looks just like it. So don't get upset. That would be, you know, when you do this right here, you're talking about, oh, I follow you. You're doing a u sub as a natural log? You're exactly right. I apologize. I was thinking it was inverse trig function. But it involves a u sub, right? That's what he's saying. So you're outstanding, actually. So correction. He knows exactly what's going on here. When it does involve a u sub, I'm going to go off to the side. Which power is higher, the x squared or the x? Just so you're knowing, like, how do I work this u sub? I'm going to let the u equal 1 plus x squared. So yeah, now you're realizing when you're doing integration by parts, one challenge that may come up at the end is when you're doing this integral part, you might have to apply the integration, the u sub or substitution rule. I'm going to let the u equal to 1 plus x squared. Because this had a higher power by 1 than this x. What's du? 2x dx. And when a 2 popped up, so what I'm going to do is divide the 2. I get 1/2 du equals x dx. x. I'm doing this so I can knock out the x dx. Andrew, super job because you're 3 steps ahead of us. You're seeing in the end where this is going. You saw this, you saw. Because now, what's going to knock out this 1 plus x squared and get substitute for it? Just a u. And what replaces the x dx? The one after u. So this gets replaced by the u. Okay, your u. And the x dx gets replaced by what? Let's put it with value. What's going to replace that? Substitution. The 1/2 u. So you now have an integral of 1/2 du out here, and you got a 1 over u. I'll get out of the way so we all can see this. Get out of the way so we can read that. Flatten this too. Let's only read that well. Half du for the x dx, that's gone. 1 plus x squared just got substitute that u substitute for it. And then the integral of 1 over u is natural log. This is what Andrew's talking about, so very good. Now I'll just draw an arrow. So what's this final answer? X inverse tan x minus 1/2, and the integral of 1 over u is natural log of u. Okay, this is where we put the absolute value bars. But don't leave the answer like this, because we did do a u sub. We're doing an indefinite integral. I have to put back what I let u equal to. So what goes right there?
1 plus x squared.
Yep. I'll put that. So x inverse tan x minus 1/2 natural log 1 plus x squared with bars around it plus a c plus a constant. There's the final answer. Okay, let's do another one of these. I mean, almost identical. I'm just going to make this angle right here, with that argument right there in the parentheses, like a 2x or a 4x or a 6x or something, so we could deal with something a little bit more challenging. When we get down to here, we're like, oh, chain rule. All right. Hey, one more thing, if you want to do this, isn't 1 plus x squared, no matter what, in the real number system, always going to be positive for any value that gets substitute for x because of the x squared?
Yeah.
So if you wanted to, what can I do with these bars? If you wanted to. You can put them soft because it's always going to be positive, right? I just wanted to note that too because that throws students off when they look at Bob. Remember who Bob is? Back of book, and they're like, you know, Professor, why sometimes they put the bars and other times they don't put the bars? They're so confused. That's why they might do that, because it's automatically going to be positive. Okay, let's do another one. It may look the same. Try that. Inverse tan of 6x. I'm going to wipe this out. Wipe it out. Inverse tan of 6x. Well, this should be the same deal. We all know what's the u. Inverse tan of the 6x. What's the dv? Just the dx. But I wanted you to take a moment, not rushing you, and try to handle that when you do that derivative. Before we said it was, oh, just 1 over 1 plus x squared. What's that derivative? Back from Calc 1. It requires chain rule.
6 over 1 plus x.
So that's where I wanted to focus. This would be the hard part. And I'm hearing it. Good job. The derivative inverse tan of x is inverse tan of 1 over 1 plus x squared. I'm hearing you do 1 over 1 plus square all this, and then chain rule. What's the derivative of 6x?
6.
6. And I'll multiply in the numerator. So that's why they're saying this right here, 1 times 6 over 1 plus parentheses 6x squared becomes, as you said, 6 over 1 plus 36x squared. And we can't simplify that. You want to think you can reduce that or anything? Hey, I do want to remind you as you're doing the work here, what's another way this can be written? Yeah, just so, you're gonna see this in the textbook as well. This means what? The same thing as this. And so when you see that, it's up to you what way you want to write it. If you want to keep everything, just keep writing arctan here, and you can do that. Or you can rewrite it like this. I wanted you, as the student, to pick the notation that you prefer when it comes to these inverse trig functions. Same thing with arc sine or arc cosine of x. They do the same thing with the inverse trig functions. So everyone, that was the challenge. Now you crush this. What's the integral of dx? Oh, let me put my dx next to this. I apologize. du is equal to 6 over 1 plus 36x squared dx. The integral of dx, not a 0, just a x, right? Because there's a 1 here. There's a 1 there in front of that d. You're like, the integral of 1 is x. Okay? U v minus integral v du. U is inverse tan 6x. You know what I'm going to start doing? I'm going to write it like that other notation. Just so students do get to see it. Arctan 6x is my u. The v is the what? X. I'm going to write that in front. So I'm going to put the v right here in front of it. X arctan of parentheses 6x. I did put the parentheses around the 6x because if I don't put the parentheses, you might think I just have arctan of 6. Minus the integral of x times, here we go, a 6 over 1 plus 36x squared. Well, let me rewrite this other side. Arctan 6x minus, looks like you got a 6x over 1 plus 36x squared dx. So all we now have to do is take care of that 6x over 1 plus 36x squared. And it's another u sub, right? We're going to get another natural log. Get that right. Now here's a u sub. So in the middle of the integration by parts problem, where I had to apply chain rule, I get down to this step. We've done a few steps already, obviously, and I have to use a u sub. I let u equal to 1 plus 36x squared. The du is, what's 36 times 2? 72x dx. I am now going to divide that 72. 1 over 72 du equals x dx.
You would want to have the 6 with the x.
Yeah.
12. 1 divided by 12.
Great call. I'll leave it like this and take care of it, but Andrew, I'll go back once I write that and tell everyone your suggestion, because they may prefer